Today I will be talking about the long-time behavior of a thermoelastic Bresse system in the absence of a second spectrum, the well-posedness and long-time behavior. This talk was presented last week in the American University of Sharjah in their fourth conference, international conference, with some modifications. This talk or this work is in a collaboration with two of my colleagues, Ahmed Khaddi from Algeria and Mohamed Al-Hiyan from La Rochelle, France. So let me see. Okay. This is the outline of my talk. I will give some introduction. Then I move to the existence and the uniqueness of solutions. After that, we talk about the exponential stability in the case of equal speed. And then when we have no equal speed, we'll talk a little bit about polynomial stability, and then I give numerical approximations. Let me mention that I will not really go in details of proofs. Those who are interested, I can send them my paper, which has been published lately or recently, and the calculations are very easy to follow. So it is well known, okay, that Bresse system is given by the following three hyperbolic equations. This has been introduced by Bresse in 1959, where phi, psi, and omega are the transfers or the displacement. Then psi is the shear angle displacement. Let me see, there is something here. Okay, very good. Displacement, and omega is the longitudinal displacement. F1, 2, 3 are external forces, and N, Q, M are the axial force, shear force, and the bending moment. Then we have to give, also these are some physical constants involved in the equations, where R here is the radius of curvature, because the Bresse system, sometimes they call it also the arc or arch system, where we take in consideration the bending. Okay, so there is some kind of bending. So you have a curvature and the radius of curvature. Here L is 1 over that curvature. And this is why if you have no curvature, you have something like this, then R will be infinity and L equal to 0, and we will see the Bresse system will reduce to the well-known Timoshenko system. The other quantities like E, G, K are physical constants like Young modulus, modulus of rigidity, transverse shear, and so on. Now, in the if we just substitute in the previous system by the values or the expressions of Q, M, and N from here, we get this system. And this is called the evolution Bresse system, because you have what you have here is an evolution equations, 3 of them, and in fact, these are coupled, three coupled hyperbolic equations. This system, for different or various values for the external forces, F1, F2, F3, and mainly used as dissipations, external dissipations, or internal dissipations. This system has been discussed by many researchers. And I'm just giving some names here as a representative from different schools, European schools, American schools. Also, we have Brazilian schools, the Middle Eastern schools, including Turkey itself, and so on. So many people discuss this system. In fact, the main feature for this system here, in order to have in the presence of, in the presence of linear, frictional damping, viscoelastic, Fourier heat, damping, and so many of these, the main observation is that we cannot have exponential decay, and that's what the best decay you can get unless you have equal speed of propagation. And these are the equal speed of propagation. So you need the equal speed between the equal between the three speeds of the wave shear. So you will get like kappa 1 over rho 1, kappa 2 over rho 2, kappa 3 over rho 1, and since we have kappa 1 equal to kappa 3, so we have equal. And the exponential decay cannot hold unless you have these. So these two conditions are sufficient and necessary condition for the exponential decay. Also, there are, in the case of if we substitute, for instance, the heat equation, the Fourier's law by Catania's law, there is some number called the stability number. It's a bit long number, and people also discussed some other models, for instance, Pipkin-Gerton and so on, and they provided the stability number. So the idea here is exponential decay with the presence only one frictional damping in the second equation. This is the condition. But if you move this to the transverse displacement, which is the first equation, then you can have also absolute, the exponential decay under some also relations between the parameters or the coefficient of the system. However, if we put it in the third equation, if we put the damping in the third equation, there will never be any exponential. So exponential stability cannot obtain regardless to the parameters. You can see so many results in this direction. I advise, for instance, by the work or the works of Isa Gasmiya. As I said, if you remember, I told you if we ignore the curvature, which means that there is no curvature, L will be 0. And as I mentioned, this Bresse system will reduce to the well-known Timoshenko system. And now this is what we have. The Timoshenko system is also a system of two coupled hyperbolic also equations in which the vertical displacement has gone, and we will have the transverse and the angular rotation here. Again, the same property was not in this case. If we put the damping here in the second equation, then we can have the exponential decay under this condition, the equal speed propagation. And if we put it in the first, we can have also the absolute, the exponential decay under some condition or equality, a relation between the parameters. You can see, for instance, also in this direction, some schools like Aqil and Shitur from France, also Ghadir and Wabi from Lebanon, from the Saudi University, we have Appalara, and there are so many people also there. I'm just giving some, as I said, representatives from different schools in the world get interested in Timoshenko system. Timoshenko system really gets the interest of so many people, and still people are working on that system. And this is the idea. The idea is that the exponential decay cannot obtain unless you have equal wave speed. But this physically is unacceptable. Physicists did not accept this, and they said this is a hard requirement, and we cannot require on the material to have this. It may happen, but it's not realistic. And in order to, and they gave some explanation why is this in the model itself. So they said this is, as I said, from the physics point of view, it was shown that Timoshenko system, the previous system, is characterized by two natural frequencies that yield a paradox known as the second spectrum. They call it second spectrum because of these, the presence of these two waves. And they showed that the rotary inertia and shear deformation included in the Timoshenko model, that model lead to a hyperbolic equation with finite wave propagation because it is hyperbolic, and it's starting from the first spectrum of natural frequencies. And they gave too many explanations, and after that they tried to give other alternatives. So in fact, what they call here the vibration theory. If you go to any book of vibration theory, you can see a lot of explanation and objections about this model as is. So in order to fix this, some other models have been given. One of them has been introduced in 2009 by Eleshkov, who replaced it here. Remember, this is the first equation of Timoshenko. This is the second what we had there. It was rho 2 psi tt. So he did some calculations and substituted that by this. Okay. So under several damping terms, various stability results of system 5. Now this system 5, let me just get rid of this if possible. Okay. Have been some stability results have been established irrespective to this system parameters. Let me give you some examples. So without putting any conditions on the parameters under, for instance, K, kappa 1, rho 1, kappa 2, rho 2, without any condition, there are so many stability results, including the exponential results. So let me give you first, let me talk about this, which we call the shear model. And the shear model, so they just removed the psi tt. They removed it. And in this case, what you have only one hyperbolic equation that requires that gives you the finite speed, but the second equation is only an elliptic equation. Okay, so it is elliptic in psi. So they discussed briefly the well-posedness, and they proved an exponential decay without imposing any relation now. And it is clear because we cannot impose any relation because we don't have any other second speed. There is only one speed, and that's it. Appalara considered the system of introduced by Eleshkov, but here he made the coupling or the dissipation through the heat equation, okay? But this is the Fourier law. And you see here, okay? And again, he established an exponential decay regardless to any relation between the parameters or the coefficients of the, okay? The next, okay, next I discussed myself. I took the system discussed by Tijani, Apalara, exactly this system you see here, but instead of having the heat equation, we used the heat system. So we used Catani's law instead of Fourier's law. And here we introduced the new way, because you see this equation now, this is evolution equation, this is evolution equation, this is evolution equation, but this one is neither hyperbolic, and this is hyperbolic first order, this is hyperbolic second order. Anyway, we did some change, okay? We introduced some new differential operators, and we established the well-posedness, proved the exponential decay without imposing again, even with the, you see, in the original Timoshenko system, if you have the coupling through the Catani's law, you cannot have exponential decay even under the equal speed propagation. You need another, okay, relation called the stability number. But here, once we move it to this new, okay, this new model given by Elishkov, then we could establish the exponential decay without any relation between the coefficients. Of course, there are the conditions, physical conditions, that these must be positive numbers and so on. And we provided some numerical illustration. So that's for Timoshenko. Also lately, we had the same result, but instead of using the, for instance, the model, Fourier's model or Catani's model, we use what we call double lag, okay? So also here, this is another model, heat model, and we prove it the same. We could get the exponential decay without any relation between this coefficients. If you want to see more results, there are so many results by my students and some of our colleagues from Brazil, Ramos, other colleagues from Algeria, and so on. So there are so many of these results. Now, okay, so motivated by this truncation, this, you see, this is called the truncated Timoshenko system. Motivated by this, and considering Bresse to be an extension, because Bresse is an extension to of Timoshenko. So provided just because motivated by that, we try to consider now this shear or truncated Bresse system. So instead of, so if you forget about this equation here for the time being, and you consider only this without this is Timoshenko. But we know that Bresse is an extension. So motivated by that, we considered for the first time, to the best of our knowledge, a truncated or shear Bresse system. And we would like to see if we can have an exponential decay. Of course, before we talk about any stability or decay, better to make sure that we have the existence of solution and uniqueness possible. So we considered these boundary conditions, these initial conditions, and now let's talk about the existence. So what we did, we in a way motivated again, but what we did for heat equation, we wrote psi, because the original system here has psi. So we wrote psi in terms of phi and omega, and of course through an operator, because you see you have the differential operators, and then we substituted here and here, and as a result, this is what we get. We get a system, okay, a hyperbolic system, these two hyperbolic, and we are considering, by the way, here Catania, but in another work, we considered also, we're considering Fourier's law as a starting, and then we considered Catania. But here I'm just going to talk about our result with the Fourier's law. So these two are hyperbolic equations coupled, and then both of them are coupled with the heat equation, which is, of course, known, this is a parabolic equation. And as usual, we have to put phi t to be some psi or some whatever, and we consider, as I said here, these are operators. Beta, this script beta is an operator given by this. And what is S? This is S that, allowed us to write psi in terms of phi and omega and get this system. Okay, we consider these spaces. We know, people know these are classical Hilbert spaces. This one is the L2 with of functions with the zero average. And then H1 star is this intersection. And then we introduce this Hilbert space, which will have how many components? 1, 2, 3, 4, 5. So we consider now this verify phi. This is equipped with this inner product. And you can just verify this is an inner product. And then we considered our system, we wrote it in term of operator, okay, UT, capital UT, A, U is given by this, where the domain of U is this. So this is, we are going to use the semigroup theory. Those who are involved in semigroup theory, they can see where I am heading. First, okay, we have to show, okay, this is our result for the existence. If we take the initial data in the state space H, then our problem has a unique weak solution, okay, which is continuous with values in this state space H. Moreover, if you take the initial data a little bit more regular than in the domain, then you will have a strong solution. To prove this, we are going to use Haley-Yoshida as expected. First, we show that A is the dissipative. So for any U in the domain, if you consider AUU, you just write it down, you do some calculation, integration by parts, you use also the definition of this operator. This is what we get, which shows that A is, okay, dissipative. Then we have to show that A is maximum. And that is, in a way, we have to prove that the identity minus A, I minus A is surjective. And here we are going to use, in fact, the lax milligram, okay? We are going to write some variational problem, and then we show the existence of weak solutions. We use the elliptic regularity by the end to show that I, okay, or the identity minus A is surjective. Once it is surjective, it means A is, okay, a maximal, then therefore we use Haley-Yoshida theorem to show that our problem has a unique solution, okay? And remember, this is not exactly our problem, because this is, there is psi, okay? So there is phi, omega, theta, but psi is missing. And this is why we call this problem an auxiliary problem. So first we solved an auxiliary problem, which means we found phi, theta, okay, omega, then we have to find the psi. In order to find the psi, okay, so these we have seen. Just we consider this again space and this function, okay, this space, this set, or also it's a space, and here is our result. If we consider, okay, if we consider the initial data in our state space, then we can have the solution phi t. Now psi is there. So we are psi is there. This is the difference between, the difference between our problem and the auxiliary problem. We get now psi there. And how we do that? Because if we take the initial data in the space, then you can use the auxiliary problem to find phi, and consequently phi t, then omega t theta. And how we can find the psi? We just go back and use that operator. We solve this problem, okay, which is this one here. We solve it, and we find psi. This is a elliptic problem, okay, and we show that this is what we need. And that concludes the existence and uniqueness or the well-posedness of our problem. We move now to the exponential decay. Here we are going to use, to find the exponential decay, we're going to use the multipliers method. In order to do so, we are going to define the energy of the system. The energy of the system is in front of you, and it consists of, it's a summation of positive terms. So if the energy itself goes to zero, it means each term will go to zero. The first thing that along the solution, the derivative of this energy is negative. So it means that our energy is decreasing, but what we're looking for is a rate of decay, okay? So how we get this? This is known for people who are working in this area. You just multiply the first equation by phi t, the second equation by psi t, the third by w, and the fourth one, because we have also the parabolic equation, we multiply it by theta. And when we do so, integrate by parts using the boundary conditions, we get that result. But that's not enough, because we need to get, as I said, a rate of decay. And for those who are working in this area, it's well known that we have to perturb our energy. The energy by itself does not give us what we need. So we perturb it by terms of first order, which are in the energy itself. And the first functional I'm using is this. And the derivative of this will give me a negative term. I'm looking for negative terms of the energy. And this is the term of the energy, but with a negative sign. Again, here you differentiate, you use the equations, because I remember we are going to find the derivative of this along the solutions, okay? Because we're looking for Lyapunov if you want to find. And then we use a second one. This second one, luckily, gave us two negative terms of the energy, this term and this term, with negative sign. And that's, so far we are in a good shape. Then we go to the third perturbation, F3. F3 will give us this term, which is with negative sign, but it gave us a bad term. What is that bad term? Because this bad term here has a second order derivative. So this cannot be, this term here, phi xt, cannot be dominated or majorized by any term of the energy. And this is why I put it here. So this is like a bad term. We will take care of it. So, but it has this in front of it. This is the coefficient, kappa 3, rho 1 minus kappa 1 rho 3. These are the speeds in a way. If you divide them or say equal, this, okay? Then we go to another term, okay? Another perturbation that gave us these two, okay, negative terms. I think we are almost done if we are not done with the terms. Look, this is first order, first order. All of them are first order. None is of second order derivative. Okay, we need this. This is for those people who know that in the spectral theory, we use this to show that this not only sufficient, but also necessary. Leave this, we'll come to it later. Now, this is our theorem. Our theorem is saying, if this is our solution, be our solution, then the functional, the energy functional, E, is exponentially stable if and only if we have equal speed of propagation. Remember, in Bresse system, in the Bresse, original Bresse, we need equal speed of two, okay, of the three equations. Here we don't have the three equations. One of them is truncated. So we need only for these two hyperbolic equations. So if we have this equal, then we have exponential stability. If we have exponential stability, it must be equal. So the exponential stability is equivalent to the equal speed propagation of the two hyperbolic equations of the truncated or shear system, okay, shear Bresse system. Now, how can we show? So first, let's do this. First, take this one to be 0. If this is 0, then that term will disappear. And all what we have here are first order. So let's start with that, taking it to be 0. And this is what happened. If this is 0, then I'm going to define L to be N. It is the functional energy plus perturbations of by the functionals I introduced. And then we have to choose all these, capital N, N1, N2, N3, kappa 3, in a way so that we get the following, the equivalence. And that's easy. This is known for people. Okay, this is a routine work by people in PDE. Why? Because all these terms have only the terms of the energy. So if you make this so large, you get this equivalence. In addition to that, we're going to get, remember, we have negative terms here. So by the end of the day, this is what you get. L prime will be less than or equal to some minus some constant, the energy itself. And since we have equivalence, I can substitute here this E by L with some other lambda, of course, integrate, and we get the exponential decay for L. And once it is for L, it is for the energy. So that is well known. There is something here down, but unfortunately it seems, okay, let me, okay. There is something here down written that the exponential decay will be obtained. Why is this? Okay. So as I said here, okay. So we use, as I said, just a routine calculation, integration by parts, and so on, integration, and we get the exponential decay. So remember, we prove the exponential decay under this condition. Now we are going to say, suppose it is not equal to 0. And that is, in fact, where we are going to use this, okay, lemma or this theorem by Gerhardt and others. And for this way, usually what we are going to do, we show that there is lack of exponential if there is no equality. And also, this is well known. In a way, we are going to use, as if we are going to use Fourier's, okay, series. In this case, we're going to write down in a way the solution. So we take some f, and we are going to show that contrary, that this one goes to, it's not bounded, so it goes to infinity by a suitable choice of lambda n. So we work that anyway. I'm not going to bore you by this. It's well detailed, but it's really technical in the paper. And what we showed by the end, that this goes to infinity, though, okay, where these are bound. Okay, so we'll show that we take f, it is bounded. Okay, we computed it in our paper, it is bounded, because f, you see here, is only cosine with some constant. But we showed that the corresponding solution will go to infinity, and therefore this cannot be bounded, and that will show the other way or the other direction of this theorem. So we will have exponential decay if and only if this is equal. Okay, I will now jump, due to the time, I will jump to the case. Okay, if you have non-equal speed of propagation between the two first equations, hyperbolic equations, definitely you cannot have exponential decay. However, we're going to show we can have polynomial decay. And for this, we need a little bit more. We need not weak solutions, but strong solutions. So we are going to take the initial data in the domain so that the solution will be strong. And in this case, we are going to define the second, okay, the second order, we call it second order energy functional, which is which looks like the first order functional, but instead of phi t, you have phi tt. Instead of having this, you have, so we differentiated by t. We differentiated the equations by t, and again, this second order energy functional is decreasing. Okay, it is decreasing. And now we are going to define again, we perturb, okay, the summation of the first and the second energy by these terms, where instead of F3, we will get F tilde 3, where we included this. Remember, now this one is not 0, because if it were 0, then no need to this, because it's exactly this one. And we're using this because when we differentiate it by t, we are going to get to that bad term. And again, when we differentiate, this is what we get. And again, this is the main result. Let phi, psi, omega, theta be the strong solution. Remember now, weak solution is not enough. We need more regularity. And assume that we have non-equal speed propagation, then the energy functional E satisfies this. So it decays polynomially with this rate. In fact, we did not show that this rate is optimal, but that's what we expect, because in most of these, the rate is always of the energy is 1 over t, or if you want, the norm is 1 over square root of t. And this is what we prove. We have to choose again these constants, n and 1, 2, 3, epsilon, eta, and so that L should be positive, and it satisfies this. L prime is less than or equal to this. Then we integrate both sides. We take this to the other side, and this to the other side. We integrate, we get, and we use the fact that ET is decreasing. Remember to take it out of, sorry, I have to move it a little bit. Hopefully this will go down. Okay, it goes down. So we integrate both sides, And when we get, in this case, the integral from 0 to t, it gives me t, et, I can take it out. Sorry for that, because this is, I'm not going to touch the mouse now. And when you integrate the other, it gives you this, which is, and this is why we need L to be positive, so that I have a constant positive. I divide by t, and I will get E decreases polynomial. Just for few minutes, I'll show you what our colleague from France, he is specialist in numerical analysis. He did some illustrations. He used the, you can see here, we used the uniform partition of 0, 1 instead of 0, L. L is 1 in this case. We use the discretization. So this is finite element methods for the space, okay, variable, but for the time variable, we use the this discretization. So finite difference instead of finite element. And this is the system, okay, the discrete system, and it is in our paper, okay. And he showed that he gave also the discrete energy. So this is the, and he showed also the discrete energy is decreasing, and finally made some tests. So we took some initial conditions that satisfy, of course, the boundary conditions. Remember, theta has Newman boundary conditions. This is why when you differentiate, you get this equal to 0 at 0 and 1. And we took different, okay, we took different parameters. The first one is the c equals speed, because we need kappa 1 over kappa 1 over rho 1 equal to kappa over rho 3. And in other conditions, we use also a different, and this is what we get. Look, here, this is for test 1, this is for test 2. These are giving you the evolution of phi, psi, omega, theta, okay? And you see they are dying, going to 0. And also you need to see the energy. So here, energy in the natural energy, okay? So here, this is, well, it is exponential, okay? But also we use the natural log to see if it is line. It did not really gave us what this one here. In some other tests, we get, let me see, we get almost a line, but in a way here, we did not get, maybe we need more tests. And this is test 2. Okay, and you can see here also the decay of energy. The first one, we have equal speed propagation, second one. And here, test 1 and test 2, you can see them, that the red one, which is, let me see, I'll just go back if you allow me one. Test 2, you see I'm taking rho 1 equal to rho 3, okay? So, okay, kappa 1, kappa 2. So here we had, in a way, to see the difference, but it's not really the tests. That's why I did not include them last time, but the tests needs a little bit more refinement, okay? As a conclusion, in both tests, we observed that the numerical solutions converge to 0. They converge to 0 for sure, but we are not getting the theoretical for the time being. Okay, these are some references. Thank you very much. تشكرات.